Hello everyone, it's a great pleasure to be here to bring the report on Kyber's failure probability analysis. There are two key points to our work. The first is to improve the failure probability analysis in Kyber's without independence assumption. We want to explore how much this assumption, which makes the original analysis not tight, affects the results. In addition, Kyber has been identified in the fourth round of NIST as the standardization algorithm for channel encryption used when accessing secure websites, and its performance in practical application scenarios is noteworthy. We're concerned about the difference between the probability of decryption failure of a specific public key and the probability of decryption failure in the meaning of mathematical expectations. This difference affects the choice of the actual public key. The presentation is divided into 5 parts. Firstly, I will introduce the post-quantum cryptography and its importance. Secondly, I will introduce the research background of Kyber, including its current failure probability analysis progress and the estimation method it adopts. After that, I will introduce the analysis method we give and discuss the current attack scheme based on Kyber's failure probability. These discussions will illustrate the importance of the failure probability analysis method we give. By comparing the analysis conclusion we give with the conclusion of Kyber's original paper, we can intuitively see its necessity in practical applications. In recent years, there has been a substantial amount of research on quantum computers, which is machines that explore quantum mechanical phenomena to solve mathematical problems that are difficult or intractable for convolutional computers. If large-scale quantum computers are ever built, they will be able to break many of the public key crypto systems currently in use. This would seriously compromise the confidentiality and integrity of digital communications on the Internet and elsewhere. The goal of post-quantum cryptography is to develop cryptographic systems that are secure against both quantum and classical computers, and can interoperate with existing communication protocols and networks. The question of when a large-scale quantum computer will be built is a complicated one. While in the past it was less clear that large quantum computers are a physical possibility, many scientists now believe it to be merely a significant engineering challenge. Some engineers even predict that within the next 20 or so years, sufficiently large quantum computers will be built to break essentially all public key schemes currently in use. Historically, it has taken almost 2 decades to deploy our modern public key cryptography infrastructure. Therefore, regardless of whether we can estimate the exact time of the arrival of the quantum computer era, we must begin now to prepare our information security systems to be able to resist quantum computing. Consequently, the search for algorithms believed to be resistant to attacks from both classical and quantum computers has focused on public key algorithms. Lattice-based cryptography is crypto systems based on lattice problems have received renewed interest for a few reasons. Exciting new applications, such as fully homomorphic encryption, code obfuscation, and attribute-based encryption, have been made possible using lattice-based cryptography. Most lattice-based key establishment algorithms are relatively simple, efficient, and highly parallelizable. Also, the security of some lattice-based systems are provocable secure under a worst-case hardness assumption, rather than on the average case. On the other hand, it has proven difficult to give precise estimates of the security of lattice schemes against even known cryptanalysis techniques. Besides, there are code-based cryptography, multivariate polynomial cryptography, hash-based signature, and others. In July 2022, NIST announced that the Crystal's Kyber algorithm was chosen as a general encryption algorithm for accessing secure websites. One of its advantages is a relatively small encryption key that can be easily exchanged between two parties, and its speed of operation. Behind this advantage, the security problem that Kyber may be faced is noteworthy. In addition to the very competitive speed, small parameters, and being based on a well-studied problems, the unique advantages of Kyber are the implementation of Kyber is easy and the scalability. For the implementation, optimized implementations only have to focus on a fast dimension 256 entity and a fast cacao permutation. This will give very competitive performance for all parameter sets of Kyber. As for the scalability, switching from one Kyber parameter set to another only requires changing the matrix dimension, which is defined in most C implementations. The noise sampling and the rounding of the ciphertext via different parameters to the compress function. Compared to other post-quantum schemes, firstly consider SIDH. The downside of SIDH is that it is more than 2 orders of magnitude slower than Kyber. The scheme is also rather new, which makes it hard to make definitive comparisons. In the coming year, both implementation speeds and quantum attacks against SIDH can improve, which may result in faster schemes and larger parameters. And for the code-based KEMs, the code-based KEMs has less conservative choices, like quasi-cyclic medium-density parity check codes are a closer competition in terms of performance, but suffer from the fact that for efficient parameters at high security levels, they don't achieve negative failure probability, which precludes their use in CCA-secure KEMs. Before discussing security issues, let's review the failure independence in individual bits of the transmitted message and the possible security impact of decryption failure rate. Danvers proved that the independent hypothesis applies to the scheme without error correction, but it may be underestimate the failure probability of the algorithm using error correction codes. Generally speaking, when calculating the failure probability, the method using is to treat the failure of each bit as independent and calculate the probability of failure on one bit. After that, treat it consistency bound as the probability that all bits can be decrypted correctly. However, the fact this hypothesis is ambiguous, and this assumption also brings inconvenience to the estimation of the failure probability of a specific public key. For the recommended parameter set, the failure of the Kyber decryption procedure are pretty small. For Kyber 512, 768, 1024 according to the NIST security categories 1, 3, and 5. The decryption failure claimed are about 2 to the power of negative 139, 2 to the power of negative 164, 2 to the power of negative 174 respectively. However, this does not give much information about the distribution of decryption failure. When a secure website selects a public key within a certain range, its corresponding decryption failure probability may derive from this expected level, and the secure websites cannot know whether the decryption failure probability of the selected public key is higher or lower desired level. For example, consider the gamma distribution. We know that X obey gamma alpha beta. The expectation of X power k is equal to gamma alpha plus k divided by gamma alpha times beta power k. Therefore, if we randomly choose a public key, the actual distribution of the failure probability of Kyber 768 is gamma 2 to the power of negative 170 2 to the power of 6, which is the blue line in figure 1. Then the probability of getting a low error rate is higher than the case of gamma 2 to the power of negative 172 2 to the power of 8. That is, when a secure website picks a particular public key that is less secure, it is more vulnerable to the attacks on the search for failures. Failure searching attacks are considered to be an important class of attacks for lattice-based schemes that require error correction. For example, Guo et al. Proposed a key recovery attack against LWE-based KEM schemes that use error correction codes to lower error probability. Bindel and Shank showed that the adversary could use the first successful decryption information to increase the probability of getting the subsequent successful decryption. Danvers et al. Showed that the effect of decryption failure on the security of lattice-based encryption schemes, and they attacked many NIST candidates' encryption schemes. The results show that the attack will significantly reduce the security of the lattice-based encryption schemes with a relatively high failure rate. In April 2022, Matzov proposed an improved dual attack based on Guo and Chalmers, which is more efficient than the primal attack, as shown in Table 1. The Matzov's work shows that the security level of Kyber is all lower than the required security level by NIST. Since the dimensions for free trick and the trick of producing many short vectors in one string will also affect the bootstrapping of the search of failures, this result reinforced the possible impact of the failure probability attack. The tight and actual failure probability analysis method we give can avoid the possible risk of attacks caused by the decryption failure to the greatest extent by adjusting the specific public key. Let's see how it works. Refer to Kyber's algorithm documentation. Its key generation, encryption, and decryption algorithms are shown in the following figure, where the compression function and the decompression function are also shown here. It can be seen that the compression and decompression function is relatively simple, which made Kyber efficient. When compress_q or decompress_q is used with x in r_q or x in r_q 2 to the power of k, the procedure is applied to each coefficient individually. The main reason for defining the compress_q and decompress_q functions is to be able to discard some low-order bits in the ciphertext, which do not have much effect on the correctness probability of decryption, thus reduce the size of ciphertext. The compress_q and decompress_q are also used for a purpose other than compression, namely to perform the usual LWE error correction during encryption and decryption. More precisely, the encryption procedure, the decompress_q function is used to create error tolerance gaps by sending the message bit 0 to 0 and 1 to rounding q divided by 2. Later, on the decryption procedure, the compress_q function is used to decrypt to 1 if v minus s transform u is closer to rounding q divided by 2 than to 0, and decrypt to a 0 otherwise. Decryption failure refers to an event in which the correct ciphertext cannot be successfully restored during decryption after the decryption steps described in the algorithm are performed. For Kyber, it gives 3 parameter sets according to the NIST security categories 1, 3, and 5. The decryption failure claimed are about 2 to the power of negative 139, 2 to the power of negative 164, 2 to the power of negative 174 respectively. The decompression after compression leads to possible errors in the algorithm. As seen in Table 2, n is set to 256 because the goal is to encapsulate keys with 256 bits of entropy. That is, use a plain text size of 256 bits in Kyber. Smaller value of n would require to encode multiple key bits into one polynomial coefficient, which requires lower noise level and therefore lower security. Larger value of n would reduce the capability to easily scale security via parameter k. And they choose q as a small prime satisfying n can be divided by q minus 1. This is required to enable the fast entity-based multiplication. There are 2 smaller primes for which this property holds, namely 256 and 769. However, for those primes, they would not be able to achieve negligible failure probability required for CCA security. So they choose the next largest, that is, Q is equal to 3,329. K is selected to fix the lattice dimension as a multiple of n. Changing K is a main mechanism in Kyber to scale security, and as a sequent efficiency, to different levels. The remaining parameters eta_1, eta_2, d_u, and d_v were chosen to balance between security, ciphertext size, and failure probability. Note that all 3 parameter sets achieve a failure probability of less than 2 to the power of negative 128 with some margin. They discuss this in more details in their paper. The parameter eta_1 defines the noise of S and E and of R. The parameter eta_2 defines the noise of E_1 and E_2. They discuss the reason for setting eta_1 is larger than E_2 in the Kyber 512 parameter sets in their paper. The failure probability data is computed with the help of the Python script, which is available online at their websites. For the theoretical background of that, we also give a presentation in our paper. However, in their script, they doesn't consider the independence of these bits, and this is our advantages. Through the mathematical tricks given in the paper, we finally reduce this expression to a tied region. Let A_I is equal to 2 to the power of D_I divided by Q, and ARE_1S is selected from certain distributions. Let A_1, R_1, and S_1 be the matrix form. We have the infinity norm of the sum is less or equal to the bound over the specific ring, where A, R, E are polynomials. By comparing the failure probability calculated by the above formula with the results claimed by Kyber, we will see that the failure probability for most samples is lower than the expected value given by Kyber, and the mean of the sample is less than the median of the sample. Specifically, for Kyber 512, the mean and median sample error rates are approximately equal, and both are lower than the expected failure probability given by Kyber. For Kyber 768 and Kyber 1024, the original expected value is the largest, followed by the median, and the mean is the smallest value. This means that the failure probability for most of the samples is lower than Kyber claims, and the probability density function is close to left-skewed distribution. From the histogram below, we can get some detailed observations, including the highest failure probability, lowest one, and others. It can be seen that there are still some cases where the failure probability is higher than the results claimed by Kyber, and this kind of public key should be avoided when selecting the public key. Finally, let's look at a demo of how our work will help the head of the security department choose the appropriate public key. The question is, the secure websites want to find a suitable public key. What can they do? The person in charge randomly generates 1,000 metrics. Then, the group tests the failure probability corresponding to the first 3 metrics. At this time, the script will display the expected value of it at the same time. After that, he entered all the metrics into the script. The script calculated that the 682nd matrix has the lowest failure probability, which is 2 to the power of negative 238. It is much smaller than the expected value, so it is recommended to use this matrix. Thank you for your listening. Thanks for listening. And these are the references.